next unit is going to be on counting and probability. We're going to discuss a variety of topics, including discrete probability, counting techniques that will allow us to actually calculate more types of probabilities. We're going to have a visual representation using Venn diagrams. We'll discuss principle of inclusion, exclusion, and then do more of the counting techniques, including permutations and combinations. Now, this type of counting isn't your regular 1 + 1 = 2 type thing. We will actually answer quite complex questions. Here's just some sample of the types of things that we are going to be looking at. For example, how many bit strings of length 17 have exactly 7 ones? We can, of course, list them all, but that would take a while. Are there more efficient ways to do so? What is the probability that two randomly chosen strings of length 16 will differ in exactly one position? Something that is important in, for example, error correcting. Why is two-factor authentication that you see everywhere now between banks and the Canada Revenue Agency logins is better than one strong password? So in order to do that, we need to lay some foundations about the concepts that we're going to be discussing. So first up, what is a random process? A process is random if it is impossible to predict with any kind of certainty what the outcome will be. So some examples here will be coin toss. We have no idea if we toss a coin, if it's going to be head or tails. It's going to be a random outcome. Or, for example, rolling of a die. Now, this assumes that neither the coin nor the die is actually unfair, right? So we truly have no idea what is actually going to happen. Now, in other definitions, we're going to define an experiment and the outcome. An experiment is an activity with an observable result, so something that we should be able to actually register. So, for example, an experiment can be a coin toss. Right? If we toss a coin, we should be able to see what the result of that is. Each possible result of an experiment is what we call an outcome. So, for example, one of the outcomes of a coin toss will be heads. Another outcome can be tails. And that leads to the next question of defining all possible outcomes. The set of all outcomes of an experiment is called a sample space. And we usually denote it by S for sample space. An event is a subset of that sample space. So you're already seeing why it was important that we learned about sets early on, so we can actually use set notation and set operations in later parts of the course. So let's think about, for example, the roll of a die. Our experiment can be rolling of a single die. Now, normally, if it's not specified, the die is going to be assumed to be six-sided. Okay, so I'm going to write it out here, but by default, we assume it's 6 sides unless otherwise stated. A sample space for this experiment is going to be a set, as per definition, of all the possible outcomes. So if I roll a single die, what are my possible outcomes? I can roll a 1, a 2, 3, 4, 5, or 6. The set of all the possible outcomes is my sample space. An event is going to be a subset of it. So if I take any kind of subset of it, for example, 1, 2, 3, that's going to be an event. Now, a lot of times we actually describe an event with another means. So for example, an event can be rolling an even number. In that case, we can list all the possible outcomes. And here it will be 2, 4, and 6. And of course, you can see that this is, in fact, a subset of the sample space. Okay, so we either define it by listing the specific outcomes we're interested in, or maybe given a verbal definition. Try to go through the exact same notions using the coin toss, or maybe try it with 2 coin tosses and see what you come up with. Once we have this in place, we can talk about probability. The way we define a probability is by just saying that it's some kind of numerical measure of the likelihood of an event. So if I have an event denoted E, so for example, rolling an even number on a single die here, the probability of that happening will be denoted by P of E, probability of the event. Now, in general, there are three types of probabilities. There's logical probability. That's the probability that's going to be obtained by calculations. So this is something that we are actually going to look at in this course. All of our probabilities are going to be of the logical kind. And in fact, ours are going to also be discrete. There's empirical probabilities, and that is something that we can obtain by sampling and inferring. So this is the types of probabilities that a lot of statistics courses talk about. If I sample a small percentage of population, can I say something about population as a whole? So if I sample 100 people, for example, on likelihood of them coming in contact with somebody with COVID, can I say something about 1,000 people in that exact same situation? Okay, sampling and inferring. And there is a very popular judgmental probability. This is what we normally call an educated guess. So something that maybe you've observed something in the past and you have a hunch about how that's going to go, but you don't really have any real rigid data to support your calculations. It's simply a guess. Again, in this course, we're going to deal with the logical. In lots of statistics courses, you're going to deal with empirical. We, in mathematics, generally do not care about judgmental probabilities. No matter what, for any event, the probability will always be between 0 and 1, where 0 corresponds to the event certainly not happening, and 1 corresponds to event certainly occurring. Now, if we are going to obtain our probability by calculations, what are those calculations going to be? So here is our first probability formula, and in fact, it is very general. We will see how it applies to a whole plethora of cases, but the overall formula, the calculation, the general setup will not change. So I'm going to start with S, which is a finite sample space. So for example, 1 here. It's going to be a space of all the possible outcomes, and we are assuming they're all equally likely. So your die is not loaded, your coin is fair, all of the possible outcomes are as likely to occur as another one. And I'm going to assume that E is an event in S, so it's some kind of subset of the, in fact, sample space here. Then the probability of that event, denoted P of E, is calculated using the following rule. We're going to take the number of desirable outcomes and divide it by the number of total possible outcomes. So in the set notation, the desirable outcomes are going to correspond to my event E, and the total possible outcomes are going to correspond to the set S. Now I'm talking about the number of in each one, so I'm interested in the number of elements in each set. So the notation for that, there's a couple of different notations. We can denote as N of E, so the number of elements in E divided by N of S, or the other notation that's used in the book is the vertical bars. So vertical bar, E vertical bar, kind of like an absolute value. There's no absolute value for a set. This is the notation for the size of the set, the number of elements within it, otherwise also known as cardinality of the set. So the number of elements in E divided by the number of elements in S. Again, this general rule will hold throughout. This is how we're going to always calculate logical probabilities. The way we actually come up with the numbers for the sets themselves is going to differ from example to example, but the formula will always stay the same. So let's see how we can use this in specific cases. So in our first example here, I'm going to roll a 6-sided die, and I would like to find the probability of rolling an even number. So because it's my first example here, I'm going to write it all out. So overall, my experiment is rolling a 6-sided die, and therefore my sample space are all the possible outcomes, and I've already actually listed them on the previous page. So this is all of the elements in my sample space. The event is going to be rolling an even number, and again, as per the previous page, I already know what what that set looks like, I'm going to calculate the probability. So probability of E, or probability of rolling an even number, is going to be the number of desirable outcomes, which is all of these. So the number of elements in the set E divided by the number of all the possible outcomes, which is the entire sample space. 1, 2, 3, 4, 5, 6. So the number of elements in this set is 3. The number of elements in this set is 6. So overall, I can simplify and I'm going to get 1/2. Now notice that, let's go back to the previous page for a second and to this formula here. E being a subset of S means that the size of E will always be at most as big as S. So the number on the top will always be less than or equal to the number on the bottom. So this number here will be smaller or equal to the number on the bottom, which means, like in my example here, it's 1/2, or in my raw calculations, 3/6. This is why I'm always going to end up with a number between 0 and 1, because the most that can happen is I'm going to have something like 6/6. Otherwise, the number on top is going to be less than a number on the bottom, so I'm guaranteed that my probability will be less than or equal to 1. If you end up with something bigger than 1, then you've made an arithmetic or a counting mistake somewhere, so please go back and check. Probability cannot exceed 1. Let's take a look at the next example. We're going to roll an 8-sided die, and we would like to find the probability of rolling an even number. I'm going to skip the step of separately writing out what happens and go directly into the formula. So I would like to see an even number. And again, my formula is the number of desirable outcomes. So desirable outcome here is an even number on an 8-sided die. So 2, 4, 6, 8 divided by the number of total possible outcomes of rolling an 8-sided die. Well, anything from 1 all the way to 8 is possible. So here's what I have. The number in my event here is 4. The number of all the possible outcomes is 8. So overall I have 4/8, or again, if I simplify, it's also going to simplify to be 1/2. Okay, let's take a look at the next one. We're still going to roll an 8-sided die, and we're now looking for the probability of rolling at least a 6. Okay, so probability of seeing at least a 6 is, once again, our formula, number of desirable outcomes. The desirable outcome is rolling at least a 6. So at least a 6 means I'm going to roll 6 or up. Now my die is 8-sided, so the highest I can go to is 8. So at least a 6 means 6, 7, or 8 divided by the number of total outcomes, which of course will be still all the possibilities here. The number of elements on the top is 3. The number of elements on the bottom is 8. So overall, I have 3/8. Notice that once you have fixed your experiment, the denominator in this formula will not change because your sample space is attached to your experiment. So if your experiment is rolling a 6-sided die, you already know that your denominator will be 8 no matter what. Your desirable outcome will depend on your event and therefore will change from one example to the next. Let's see what happens in a slightly more complicated example. Here you're going to roll 2 dice, one red and one blue. Again, if it is not specified, we're going to assume that they're 6-sided die. So maybe I'm going to include that information here. But again, it's omitted. We're assuming they're regular dice. One red and one blue. So they are 2 different colors, and we're going to have to be mindful of that. First, the question asks to simply determine the sample space. So what are all the possible options that we're going to see if we roll these 2 dice? Now, how are we going to actually record this? We're going to think a little bit more carefully here because the 2 dice that we have are different colors. So for example, rolling 3 on the red and 4 on the blue is not the same as rolling 4 on the red and 3 on the blue. So while the numbers that appear might be the same, the actual color of the die matters. So if we're going to record it, let's try to come up with some kind of system. I'm going to say that the first spot that I'm going to list things in represents the red die, and the second spot that I'm going to list things in represents the blue one. Then I can actually start writing things out. So what are my options? I can have 1 on both red and blue. I can have 1, 2, 1, 3, meaning 1 on the red, 2 on the blue, 1 on the red, 3 on the blue. So I'm going to go through all the possibilities of having 1 on the red die, which will of course result in 6 possibilities for the blue die here. Then I'm going to list all the possibilities that start with 2 on the red die and go through all of the options for the blue, and so on. This may take a while. The last option will be 6 on both die. If you write them out all carefully, you will notice that there's altogether 36 possibilities. Now, because writing this out as a list might not be the best way to visualize what happens, especially with questions to come, you might want to think about how to organize this information a little bit better. And one suggestion that I might have here is to put it into some kind of a table. Notice that if we decide to list in an order of, let's say, fixing what happens on the first die and then going through all the possibilities for the second, we could put this in a table like this. So 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. So my first row will correspond to my first red die, all being 1s. The second row could be all the possibilities where the red die is 2 and all the options for the blue die are listed, and so on. So fill this table out and you will see that my table is going to be 6 rows and 6 columns. Maybe let me write down all the possibilities for the beginning of the columns. And then this way we see that I in fact have 36 options if I fill the rest of it out. 6 by 6. 6 times 6, 36. So the size of my sample space here is going to be 36. What is the probability that a 3 is rolled? A 3 on either red or the blue. And the question is about probability. So we're going to think back to our formula for the number of favorable or successful outcomes divided by the total. So number of favorable or something that you want divided by the number of total outcomes. The number of total outcomes we of course already have because we've determined our sample space. It's going to be 36. So now we need to figure out what is the number of favorable outcomes, the desirable ones, the ones when a 3 is rolled. Now, we can go through the list and find everywhere where a 3 occurs and count those numbers, or we can use our table structure here because it might be a little bit easier to visualize. So notice that for this row, everything here will correspond to a 3 being rolled on the red die. And so I can fill them out, and these are going to be some of my possibilities, everything in this row, or the 3 can be rolled on the second, the blue die, so it's going to be everything in this column, and I can fill that out so that I can visually see and count all the possibilities. None of the other entries, I don't have to fill them out, but you can if you want to, will have a 3. So altogether, what are the entries that include 3s? They are this row, and they're in this column, and I need the total number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That is going to be my number of desirable or favorable outcomes here. Notice that if I just think of sort of the row and column, I am in a bit of danger to count this 3, 3 twice. But of course, 3 on the red and 3 on the blue is the same as 3 on the blue and 3 on the red. It's the only one where the order doesn't matter because the numbers are the same. So we have to be careful not to say it's 6 entries here and 6 entries here. One of those entries is the same, so instead of 12, we get 11. Next up, What is the probability that the numbers rolled add to at least 10? So again, we're looking at the probability, so we're going to look at the exact same formula. Number of favorable outcomes divided by the number of total ones. Once again, the number of total ones we have already, that's the entire sample space, so it's going to be 36. And now we have to count how many of them will add to at least 10. We can go through our handy-dandy table, or we can do a different kind of justification. Let's do both so we can see how the problem can be approached in two different ways. So, thinking of the rolls, I'm going to have a red die and a blue die. If I roll one on the red, is there anything I can roll on the blue that will produce a favorable outcome? No, because the highest number I can roll on a blue is 6. 1 plus 6 is not going to add up to 10. So this is completely impossible. If I roll a 1 on one of the colors, one of the die, no matter what I roll on the other one, it's not going to add up to 10. What if I roll a 2 on the red? Is anything on the blue going to produce a desirable outcome? No, same reasoning. 2 plus 6, because the highest number will be 6, is not going to give me a 10. So this is out too. If I roll a 3 on the red, can anything on the blue add it up to 10? No, once again, this is not a possibility. If I roll a 4 on the red, then a 6 on the blue will produce a desirable outcome of 10. Notice that nothing else on the blue will actually give me the result that I want. What if I roll a 5 on the red? What are the potential rolls of the blue die that will produce a desirable outcome of at least 10? Well, if I roll a 5, that will work. 5 plus 5 is 10. Or if I roll a 6, that would also work because 5 plus 6 is 11. So in fact, in this case, I have two possibilities, a 5 and a 6. Finally, if I roll a 6 on the red, what are the options for producing a sum that's at least 10? Here, I'm actually going to have three options. 4, 5, and 6 on the blue will give me a total sum of at least a 10. So these are my options in this order. Now I got to be really careful because I got to think about the actual colors. Here, I started with analyzing everything from the perspective of the red die being rolled first, and then figuring out what colors or what numbers on the blue die will actually make it work. But what if I started with a different one? So if I start with 4 on the blue, then my red die will have to be a 6 to produce at least a 10. And if I actually go through this logic, I will see that I'm going to end up with the exact same things, but of course for the different color. But I will also notice that I already have listed all of these choices above. Let me just make a little bit of give a little bit of the room to myself here. Notice that every possibility here already occurs here. So for example, 4 in blue, 6 in red is actually this option right here. 4 on blue, 6 on red. So I don't have to redo all of this work. All of these already occur as options over there. So I can simply take this out. This did not need to be counted, and count the favorable outcomes here. I have 1 possibility, 2, 3, 4, 5, and 6. So the number of desirable outcomes here is 6. How can we count this in our table? Where are the positions of the roll of the die in the table that are going to add to at least 10? So using similar logic in the table, I can cross out the first 3 rows, because if one of the die is less than or equal to 3, it's not going to work. And I can similarly cross out the first 3 columns, because that's not going to work either. Then what is left is this corner here. This is going to be 4, 4, so that's 8, that's not going to work. This is going to be 4, 5, that's 9, it's not going to work. And symmetrically, this is going to be 5, 4, it's not going to work. So the only positions in the table that are actually going to produce something that I am interested in are located right here. There we go. Right, so they will correspond to 6, 4, 6, 5, 6, 6, 4, 6, 5, 5, 5, 6. Here are all 1, 2, 3, 4, 5, 6 choices, and that is why I have 6 total desirable outcomes. Okay, 2 different ways to approach the same question. The answer, however, of course, should match up. Take a look at the next part. Here we're going to define 2 events. E is the event that the sum on 2 dice is 8, and F is the event that at least one of the dice has a 3 on it. First of all, let's write out all of the outcomes for each of the events. Remember that event is a subset of a sample space, so I can simply write out all the possibilities. If I have the sum that needs to be 8, I can sort of follow through with the same logic. If one of the dice has a 1, no matter how big the second one is, let's say 6, the sum is still not going to be 8. So there's no way that I can have a dice that has a 1 on it. If one of the dice has a 2, then in order for the sum to be 8, the second one has to have a 6. If one has a 3, then the second one has to have a 5. 4, 4 is another option. And then, of course, I'm going to have all of these options reverted, right? So this represents 2 on the red die and 6 on a blue one, but I also need an option where I have the other way around. So 6 on the blue, on the red, and 2 on the blue, and it's the same for this guy. I've accounted for 3, 5, I need to account for 5, 3. Now, of course, 4, 4 is going to be the same. It's 4 on the red and 4 on the blue that looks the same, no matter how you roll them. Now, F is the event where at least one of the dice has a 3, and that is already what we considered in part B here. So going through the table, I know it's going to be all of these outcomes here. So I'm not going to list all of them. I'm going to list them sort of first as a column, and then as a row, 3, 1, 3, 2, with the understanding that I am including in this set all of the options that occur here. Now, I'm asked to perform set operations on these events. Now, these are just standard set operations. We have practiced with them before. So all I'm going to do is actually perform them on these 2 sets, E and F. The intersection, of course, will be what is common between these 2 sets. Again, because I haven't written down all of this, I'm going to be a little bit careful, and I'm going to look at my set E here and think about what is common between these and these numbers that are circled in blue in my table. And I will notice that the only commonality I have will be 3, 5 and 5, 3. Now let's come up with a verbal description of what the set E intersection F actually means. Remember that the intersection stands for and. So this is the event where the sum on the 2 dice is 8 and at least one of them is 3. So let's write that down. The sum is 8 and at least one die has a 3. Now, if we actually write it out this way, we can double check whether it's reasonable that we got this as the entire, all of our outcomes for this intersection of the 2 events. And it makes sense. The sum has to be 8 and at least one of the die has to be 3. So I already see that these were my only choices that I could have picked out of E. For the next set, I have E union F. Union means an or. So I'm going to have, if I want to start with the verbal description first, the sum is 8 or at least one die has a 3. Now remember that the union means I'm going to actually have to list all the possibilities in one set and all of the possibilities with another set. So here, if I am to write this out, I can start by listing all the elements in E. So you know what, I'm not going to be able to fit it in here. So 2, 6, 3, 5, 4, 4, 6, 2, 5, 3. This is everything that's in E. So maybe I will denote it as such. And then I have to list everything that also belongs to F. Now remember, repeats and sets are not allowed, so I'm going to have to be careful about eliminating those. So what do I have left in F? I have 1, 3, 2, 3, and so on all the way. Not including, you know what, I'm actually going to list them all. So 1, 3, 2, 3, 3, 3, 4, 3. Now 5, 3 is already included here, so I don't need to list it again. And then I'm going to have 6, 3, 3, 1, 3, 2, 3, 3, 3, 4. 3, 5 is already listed, so I'm going to omit it, and 3, 6. Okay, so this is, let's call them extras in F. All right, so nothing new in a sense. We are really just working with the sets the way that we used to work with the sets. And then finally, I have here E intersection F prime. So prime is another notation for the complement, so I can replace it with a complement here so it looks a little bit more familiar to us. So I'm looking for the commonality between the set E and the set not F. So I need to have that the sum of two dice is 8, because it needs to be an E, but the die do not have a 3 on them. So purely from this verbal description, I can see that my intersection will be everything in E that does not have a 3. So 2, 6, 4, 4, and 6, 2. And there we go. In order to practice a little bit more, here's an extra example for you guys to do. The procedure is very similar, except for now my die are identical, so you're going to have to think about how that changes your approach here. Make sure you write out all of your requirements. So as we started here, write out the sample space, write out all the probabilities, all of the outcomes, and then start calculating the probabilities based on this approach of the number of desirable or favorable outcomes divided by the number of total. This is a very standard example. You should certainly do it to make sure you get more practice with these concepts. We have just seen in the last couple of pages, computing probabilities means counting the number of elements in a set, whether it's your sample space and you need to count all of the possible outcomes, or whether it's the number of desirable outcomes that you are needing to actually calculate. Now, if the sets are small, as they have been in examples so far, we can calculate it directly by simply listing all the elements and counting them one by one. But if the sets are long or have structure that is not very clear, then we will need to generalize our techniques. So let's think about how we generally count the number of elements in a set. If my set is this, 1, 2, 3, and so on, of course, counting is easy because I can see that it goes 1 element, 2 elements, 3 elements, and so on, 100 elements. So the size or the cardinality of this set is going to be 100. But when the numbers are not in order, it's going to be a little trickier because I'm not going to list everything between 10 and 100. I'm not going to be able to point my finger at each element and say the cardinal number that corresponds to it as the number of elements in the set. So we're going to have to think of what pattern they follow. The way that we normally count stays the same. This is element 1, this is element 2, this is element 3, and so on. And I want to know what number element is this last one. Notice the pattern here. I start with an 8, and that's element number 1. The next one is 9, and that's element number 2. Then we have 10, and that's element number 3. What is the pattern between 8, 1, 9, 2, 10, 3? We notice that every time I count here, I subtract a 7. 8 minus 7 is 1. 9 minus 7 is 2. 10 minus 7 is 3. And so this pattern will persist. And the last one will also be minus 7, which will correspond to 100 minus 7 being 93. So if I carry through, I can see that I've accounted for 93 elements, and therefore the cardinality of set A is 93. Let's try this with another one. If I start with 13, go all the way up to 98 in order. again, my actual procedure doesn't really change. I'm going to think of this as element number 1, number 2, number 3, and I want to know what element number is going to be this 98. So what happens in between here? 13 corresponds to 1, 14 corresponds to 2, 15 corresponds to 3. So I am here, in this case, subtracting 12. 13 minus 12 is 1, 14 minus 12 is 2, 15 minus 12 is 3, and so on. So in order for me to match this pattern, I will have to subtract 12 from 98, which will result in the number that corresponds to this last element. Now, of course, I can write this down because I can do this arithmetic in my head, but I would like to actually generalize even further. Instead of every time coming up with this corresponding, I would like to think of where these numbers actually come from. So look, if the first element in the set is 1, then it's easy because I can start counting with that. If the first element in the set is not 1, I need to subtract a number that will bring it down to 1. So in order to turn 8 into a 1, I need to subtract a 7. In order to turn 13 into a 1, I need to subtract a 12. So the number I'm subtracting is always 1 less than the number I am starting with. So instead of just writing down that the size of B is 98 minus 12, I'm going to think about how this 12 was formed out of this 13. What I have really, I'm going to write this down first, but then I'm going to notice that this 12 is actually 13 minus 1. I needed to adjust by this amount in order to bring number 13 down to 1. Right? I haven't actually changed this expression. 12 is 13 minus 1. It's just writing it down this way. I now have a point of reference to the last element on the set and a point of reference to the first element of the set itself. So my current expression depends only on the first and the last elements here. And if I perform the actual arithmetic, I should get 86, which will be my number here. That means that if I actually have a very general set where I don't even know the numbers, I just represent them by letters, so some number m and some number n here. If I think about generalizing this procedure, I will do it in the exact same way, and I'm going to think about what this last one represents. What do I need to subtract from m to get 1? I'm going to need to subtract minus m plus 1, and so on and so forth. And so, if I am to match this last, the pattern all the way to the last element here, I will notice that the size of set C, the cardinality of it, has to be n, the last element, minus m, the first element, plus 1. Okay? So let's write this out here in verbal description. So this represents last element. This represents first element of the set. And then I have to add a 1 because I'm not starting from 0. I'm starting to count from 1. So this is what this plus 1 balances out. This is the general formula that we will have. So to answer questions like these, how many integers are there from m to n inclusive? The answer in this case is going to be n minus m plus 1. Let's see how this formula works with the other cases that we've already covered here. So for this first case, again, I understand that this is very simple because all the numbers are in the exact same way as we would account them for, but let's apply the formula. The formula states that in order for me to compute the size, the cardinality of this set, I'm going to have to take the last element, which is 100, minus the first element, which is 1, and then plus 1. So the formula has a baked-in plus 1 here. So I can see, of course, that minus 1 plus 1 cancel out, and I do have the 100. So I've confirmed that my original computation was correct. Let's try with this one now. So then the cardinality of set A is, again, as per formula, the last element minus the first element plus 1. The last element is 100 minus the first element, which is 8, plus 1. 100 minus 8 is 92, plus 1 is 93. And again, our number agrees with what we got there. This seems, the formula I think usually seems just a little bit more complicated than we would expect, but the general procedure seems fairly straightforward, and it is really quite surprising about how useful it will come in a number of different applications. So let's consider the first example here. We're going to think of all 3-digit numbers. 3-digit, so we will start with 100, 101 if we're going to list them in order, all the way up to 999. These are all the 3-digit numbers because 1000 then is going to be a 4-digit number. We cannot account for that. First question asks, how many of these numbers are divisible by 5? So let's think about what the numbers are and how we can justify divisibility by 5. So let's actually write out the numbers. So again, I'm going to start with 100, 101, 102, and so on. Now, I don't want to write all of them out because the only ones I'm interested are the ones divisible by 5, right? So I know that none of these are going to be. The divisibility by 5 is easy. The number has to either end in a 0 or a 5. So the next number divisible by 5 will be 105. The next one divisible by 5 will be 110, 115, and so on. Now, what about the last of these numbers that's divisible by 5? So remember that the 3-digit numbers will go all the way up to 999. So 999 is not divisible by 5. The number before that is divisible by 5 will be 995. And then the number of 1000, which is divisible by 5, is not a 3-digit number. So I will no longer actually be able to include it in my sequence. Now let's think about the divisibility by 5, not just in terms of the patterns for the last digit, but rather of what it actually means to be divisible by 5. To be divisible by 5 means that I can write this number as 5 times something. So 100 is 5 times 20. This is my first number divisible by 5. 105 is 5 times 21. 110 is 5 times 22. My 5 doesn't change, but my multiples here actually go up by 1. And so I'm going to have 5 times 23 and so on all the way up. Now you can pull out a calculator and figure out what 995 corresponds to, or we can be a little bit sneakier and I can notice that 1000 is easy to do. It's going to be 5 times 200, which means that the multiple of 5 before it will just be 1 short. So it's going to be 5 times 199. So what I am seeing here is a clear pattern. Instead of looking at the actual numbers themselves, I'm going to look at 5 times those numbers. Because here then, I can see that the numbers that are factors of 5 go up one by one all the way to 199. So instead of counting the guys that I've listed directly, I'm going to look at the number of integers between 20 and 199. So our counting comes down to the fact that the number of numbers between 100 and 999 that are divisible by 5 is actually equal to the number of numbers between 20 and 199. And for this, we have a direct formula. Remember, the last number, 199, minus the first number, 20, plus 1. So if we compute that all together, we're going to get 180. So there are 180 numbers that are divisible by 5 that have 3 digits in them. Part B is asking about probability. What is the probability that a random 3-digit number is divisible by 5? Back to our formula. The formula suggests that we need a number of desirable outcomes divided by the number of total outcomes. So in this case, the number of desirable outcomes are the digit or the numbers divisible by 5. And we know that there are 180 of them. The total is the total number of 3-digit numbers that we're choosing from. So the numbers between 100 and 999. And for that, we will also use the exact same formula. To figure out how many numbers there are between 100 and 999, I need to take the last number, so 999, minus the first number, so 100, and then add a 1. So if I compute that all together, on top I have 180, and on the bottom I'm going to have 900. So my probability is 180 over 900. If I simplify that, it's going to be 1 over 5. And that kind of makes sense, right? The probability that a random number is divisible by 5 is 1/5. 1/5 of the numbers is divisible by 5. That's kind of also clear in this pattern here. Every 5th number is going to be divisible by 5, which means that the numbers in between, 4 of them, are not. So every 5th time, I'm going to get lucky in hitting the numbers divisible by 5, and other times I will not. It's always nice to be able to check whether your computed probability agrees with your intuition. It won't always agree with the intuition. We will see some examples of that later on. But in terms of just counting with the numbers, it often does. Let's take a look at this example with some quick exercises. I strongly encourage you to pause the video here and actually try these out for yourself by simply using the above formula. Remember our formula here. If I'm counting from m to n, the total number of integers in between is the last number minus the first plus 1. Pause the video, try to get through these yourself. Okay, so you've tried it for yourself. I'm counting from 10 to 99. Straightforward, these are just the numbers, so I'm going to take the last one minus the first one plus 1. If I'm going to count the odd integers between 10 and 99, I'm going to have to think in the exact same way, except for odd means they're not divisible by 2. So these numbers are going to be odd. Every other one is going to be odd. Follow through these calculations. I'm not going to show the work here. I am just going to write down the fact that the answer is going to be 45. And your calculations better agree with that. How many integers from 10 to 99 have distinct digits? So distinct digits means I'm not allowed numbers like 22 or 33. In fact, let's think about all the numbers that I'm not allowed. Not allowed 11, 22, 33, 44, 55, and whatnot, all the way up to 99. There are 9 of these altogether. There are 9 numbers that I'm not allowed. Everything else is allowed. It will have distinct digits. Everything else is what we've calculated in part A. There are in total 90 numbers. So in this case, I'm going to take all of my 90 and subtract the 9 that I'm not allowed, resulting in 91. How many odd integers from 10 through 99 have distinct digits? Well, I know that 45 of them are odd, and these guys are not allowed to have distinct digits. So the odd numbers that are not allowed to have distinct digits are a subset of this list here. So 11, 33, 55, and whatnot, there will be 5 of them. So 45 total numbers that are odd minus 5 that have the exact same digits will result in 40. The last one is talking about probability. So this is where we're once again going to think of our number of desirable divided by the number of total outcomes. And everything that we need has already been computed in the first 4 parts of this question. What is the probability that a randomly chosen 2-digit integer has distinct digits? So the total number here are all of the 2-digit numbers, which by part A, we know there are 90 of. So my denominator in this case will be 90 for the number of total outcomes. And my desirable outcomes are the distinct digit ones. And I know that the number of distinct ones, the ones with distinct digits, was computed in part C. Now, here I'm going to have 90 minus 9. Notice that I made a typo here, 81. So I'm going to have 81 divided by 90. So what about the next one? Has distinct digits and is odd. Again, my formula, the number of desirable divided by the number of total. The total is still going to be all of the possible two-digit integers, so still 90 of them. But now in my numerator, I have to have that they're distinct and odd, which is of course something that I've computed in part D. So on top here, I'm going to have 40. Okay, take a look at these calculations. Go back through this logic again for part B to make sure that you understand how to count factors and not necessarily the numbers themselves.